Okay, so we are now starting this new section, the fifth section of this chapter, some standard limits. So it starts like this. Armed now with the limit laws and the speech test, we can now compute a large number of limits. We already saw the limit laws in the first section, where there are some subdivisions in that result. One of which, for example, says that if we take two convergent sequences and take their sum, then the sum is also convergent and its limit equals the sum of the limits of the original sequences. Like that, there is one for product of sequences, difference of two sequences, and then quotient of two sequences, where we can divide, things like that. So that was the limit laws. And the speech test, of course, we have seen more recently. If a sequence is trapped in between two sequences, both of which are converging to the same limit, then the trapped sequence also converges to that same limit. So using these two things alone, we can in fact find the limits of a large number of convergent sequences, some of which we will find in this section. So the author starts off with this simplest example, that of a constant sequence, where all the terms are equal and they equal to a single real number, say c, and here the limit is also c. How? If we just for the sake of this argument, if we call this sequence an, then all the ans are of course equal to c. Now, in order to show that this limit is c, we apply the definition itself. For any positive real number epsilon, we want to find a positive integer n such that this distance between c and the nth term of the sequence is less than or equal to epsilon for all indices n greater than or equal to that stage, capital N. Now, in this case, things are particularly easy because this term on the left hand side of this inequality is always 0, because all the ans are equal to c, and since epsilon is greater than 0, so this inequality is true, trivially true, and that happens in fact for all the indices n. So if you want, you can take this capital N to be equal to n equal to 1 itself. So that just proves that this limit is c. And besides this, we have also seen in proposition 6.1.11 that this sequence converges to 0, the sequence of the reciprocals of the positive integers, which goes like this: 1, 1 over 2, 1 over 3, and so on. Now, this limit can and will now be immediately used to find another limit which looks like this. So that is our first result, and since in the proof of that we are going to use this limit, so it will be a corollary to this proposition. So let us start. So this is the first result of this section. We have this limit equal to 0 for every integer that means every positive integer. Note that here, instead of considering reciprocals of positive integers, we are considering reciprocals of the kth roots of positive integers. So if you in particular take k equal to 1, you are getting this result. So this is a special case of that one. But still this one is a corollary because we need this to prove this one, which now we are going to do. Okay, so the proof starts like this. We know from what is that result, lemma or corollary or theorem, lemma. Five, six, that the sequence this sequence is decreasing and bounded below by 0. Recall what we have. You can of course go back to this lemma and see what the statement is. It's about those inequalities involving nth roots of positive real numbers. It has some parts a, b, c, d like that. One of those parts says this: if x and y are both positive real numbers, then x greater than y implies the nth root of x is greater than the n, but because we are dealing with kth root, so let us just take k here. This is one of the parts, and this can be used to show that this is decreasing. It's very easy. Just you consider this inequality: n plus 1 is greater than n for all positive integers n. So the kth root of n plus 1 is greater than the kth root of n, and after this we would take reciprocals. But before we do that, let us also recall that another part of this lemma says this, that the kth roots of all positive real numbers are themselves positive. Okay, no matter what k is, no matter what x is, x to the power 1 by k is a positive real number. So that means we can take reciprocals on both sides, and that is because they are non-zero, and the inequality will get reversed because the individual real numbers are in fact positive. So that means this will imply that 1 over n plus 1 to the power 1 divided by k is less than 1 over n to the power 1 over k. And that's how we get the fact that the terms of this sequence are decreasing. The larger you take n, the smaller the term becomes. And the fact that we have just now used the fact that the kth roots are all positive. So that means their reciprocals are also positive. So that is why this sequence is bounded below by 0. So that means this is a decreasing sequence bounded below by 0. So from a previous result on this type of monotone sequences, this sequence is convergent. It has some limit. What limit, that we don't know yet, but we at least know there is a limit. So we are going to conclude that now. hence, and that is hence by, that was proposition 638. But for decreasing sequences, instead of increasing sequences. If you go to the statement of this proposition, you will see that it was stated only for increasing sequences, and it was just mentioned that a decreasing sequence version is also true. So we are going to use that part, the decreasing sequence version part. In fact, that's not the only thing this proposition says, that because this is decreasing and bounded below by 0, that a limit exists. We in fact have more information about the limit. The limit actually is the greatest lower bound of this sequence. That, however, we won't use here. We will find the limit using something else. Instead of increasing sequences, the limit L equal to exists. We are putting a colon here because we are defining L to be this limit. Okay, L means this limit. Now what we do? Now we use the limit laws. Using the limit laws, and that is theorem 6119, I think. Now by part B, actually. Part A, I think, says that the sum of two convergent sequences is convergent, and the limit is the sum of the limits. Part B is it involves product of sequences. So and induction, we have L to the power k equal to this, of course, is just simply we are writing this for L. We haven't used this yet. Now we will write the implication. It is equal to this. And that you can see is just this limit. So this is where we use that proposition 6111, I think we were mentioning. Yes. And write this limit equal to 0. So do you realize why we have written AND induction here? That is because the actual part B of this proposition just says this: if you have these two sequences, say one of them is an and another one is say bn, both of them are convergent, an converges to a and bn say converges to b, then this part says that the sequence an bn also is convergent and it converges to ab. In the particular case where both the sequences are the same, you get this limit instead. And by induction, you can change this 2 to any positive integer k. Now consider the sequence, this sequence, that means our original sequence in place of an, and in place of a, of course, you have L. So this is just this equal to this. That's what we have written. And this of course becomes 0. Okay, so that means the kth power of L is 0. So that means L itself must be equal to 0. This implies L is equal to 0. That means our original limit is 0. That's what we wanted to prove. So this completes the proof of this corollary. Then there is another one. This is lemma 652. Let x be a real number. This is also one limit that we very frequently use in analysis. Let x be a real number, then the limit limit of x to the power n as n approaches infinity exists and is equal to 0 when the absolute value of x is less than 1. This part is used quite frequently, and also this same limit exists and is equal to 1 when x is equal to 1. So these are the two situations where the limit exists, and now when the limit does not exist and diverges when x is minus 1 or the absolute value of x is greater than 1. Okay. In this statement, the word diverges seems a little strange. The limit diverges, we actually have no such concept in this book. We say that a sequence diverges if we are properly going with the definition. However, we can understand that what the author meant to say here. Divergence means the limit does not exist. That's all. And the proof of this is one of the exercises. It's the second exercise. And then there is one more. For any positive real number x, we have limit of x to the power 1 by n, 1 over n, as n approaches infinity is equal to 1. So here we are considering nth roots of x, which we know all of them exist because x is a positive real number. So from chapter 5 we know that for any positive real number its nth root exists for any positive integer n. So if we consider those nth roots where n is changing but x is fixed, then that sequence converges to 1, and its proof also is one exercise. So now next we are going to see those exercises, because here the section ends actually. So it's the third exercise. So let's now start the exercises. Oh, but before that there is something else also the author wants to say. We will derive a few more standard limits later on once we develop the root and ratio tests. For series, for convergence of infinite series. In the course of developing those tests, we will come across some standard limits which are not trivial at all, and which can be themselves be successfully used to derive even more limits which are not standard but they are still useful. Ratio tests for series. Okay, so let us now start the exercises. show that limit of 1 over n to the power q as n tends to infinity is 0 for any rational positive rational number q. So you can see that first we had the limit of 1 over n, which is 0, and then we saw that the limit of the reciprocals of kth roots also is 0, and now we are further extending that to rational powers where the rational number is positive. That limit also exists and it is equal to 0. There is hint. Use corollary 615, of course, yes. Sorry, 651, not 615. And the limit laws. That is theorem 6119. This is one theorem of which I remember the number exactly for some reason. It's 6119. And also there is another part. Conclude from this limit itself that the limit of n to the power q as n approaches infinity, this does not exist. Here also a hint is given. Argue by contradiction. Using theorem 6119E. So let us start the solution. Most often in mathematics, when we come across such exercises, such problems, hints are given. It's not absolutely necessary that you follow everything in the hint. If you can come up with your own solution, that is as good as any other solution. And why I am saying this, it is because when writing a problem in a book, the author may have something particular in mind, which may not always come to the reader's mind when they approach this stage where they are going to solve some exercise. So maybe, and it has happened in this text itself, that there is a hint, but without following the hint, if you follow some other path, then you get an easier solution. Okay, so it's not always the case that you have to adhere to the hints, whatever is given religiously. You find your own solution, and if you without looking at the hint, you try to think what a possible solution can be. Then if you are stuck, then look at the hint, and like that you should progress. And here, for example, this is a typo, of course. It's not theorem 6119e, I think. What we really need here is part B. We will see. And before that I need ink. The first limit is quite easy. It's just an application of the things we have already found. So it's straightforward. So because q is a positive rational number, since q is positive, we have q equal to a divided by b for some positive integers a and b. Next, what we do, we apply corollary 651 with for the sequence whose terms are 1 over n to the power 1 by b, that is the bth roots of the positive integers n, by corollary 651 we have this limit one over b as n tends to infinity is 0. And then what you do, you apply part B of theorem 6119 using and along with induction, that thing, to raise both sides to the eighth power, because a, keep in mind, is a positive integer. And induction, we have, let us start with this part because it will just stay 0. And then in this step we are using this theorem 6119b, and it's a generalized version that one can obtain by induction. This, and then by usual rules of exponent and bth roots, things which we have already obtained, this is equal to this, that is this, and that's how this limit is equal to 0. And now we are going to conclude from this that the other limit does not exist. Next, and we will do that by contradiction. So we will suppose that it exists and then derive a contradiction. Let the limit L defined to be equal to equal to this one, this limit. Let the limit or we can, of course, okay, we can write suppose the limit L exists, then by the limitless, specifically part B of theorem 19, zero equal to 0L. Note that the supposition that this limit exists means in particular that L is a real number. So if you multiply 0 and L, you will get 0. Now in place of this 0 we can write this limit. And in place of L, of course, we will write this one. Now the fact that both the sequences, this 1 over n to the power q and n to the power q are convergent. The convergence of the first one we have just now proved, and the convergence of the second one is our supposition. So because of that, we are in a position to use this part B and write the product of these two limits equal to the limit of their product. And which becomes the limit of the constant sequence 1. All of those terms are equal to 1. And we know that that limit is 1. So we have obtained this contradiction that 0 is equal to 1. This is a contradiction and proves that our last supposition is wrong. So this limit does not exist. So that completes the solution. Next, we come to the second exercise, which of course will be the proof of that lemma. Prove lemma 652. Here also hint is given. Use proposition 6, 3, 10. We will see what this proposition is or was. We have already seen it, but we forgot what it is. Then exercise 6, 3, 4 and the Swiss test. Okay, so lemma 652 means it's that thing. X is a real number and X is a positive real number, I think it was, no? Now X is any real number. If X is equal to 1, then this limit is 1. If the absolute value of X is less than 1, then this limit is 0. If absolute value of X is greater than 1 or X is equal to -1, then this limit does not exist. Okay, so that's what we have to prove. We need to prove these things. You see that all the possibilities of the real number X have been covered here. This case, of course, is one case. This is another case. So what else is there? This being equal to 1. There are two ways in which this can happen. Either X is equal to 1 or X is equal to -1. So those two cases have been covered here. So everything is available. So let's go through the solution. So we will first do what? We will first consider the case where the absolute value is strictly less than 1. Assume first that this is strictly less than 1. Then by proposition 6, 3, 10 is this, and now I remember. If you have a real number that strictly lies between 0 and 1, then we have already proved that this limit is equal to 0. Okay. So there will be two cases for us now. One is where X is 0 and one where X is non-zero. When X is equal to 0, the sequence is here. We are, although you see that nothing has been said about where the index starts in this limit of the sequence x to the power n, but we already saw before that it does not really matter where the index starts. When the sequence is convergent, and that does not matter, and when the sequence is not convergent, that also does not matter. Okay, so we have decided to start the index at 1. So the sequence is the Of course, the constant sequence, all of whose terms are equal to 0, and hence it converges to 0. That is, this limit is equal to 0. When x is not equal to 0, don't forget that we are under the first assumption. Under that we are having these things. So when x is not equal to 0, we have this. We already know that the absolute value of any real number is non-negative. It's greater than or equal to 0. So when the real number is non-zero, then the absolute value is strictly positive. And our assumption is that that is also less than 1. Hence, by this proposition, six, 3, 10, limit of this thing, this sequence, is equal to 0. That is, but we know that this can also be written as the absolute value of x to the power n. This thing is equal to 0. So by not the squeeze test, but by the zero test for sequences, which let us recall what the zero test was. The zero test says that if you have a sequence of real numbers, say an, then it converges to 0 if and only if the sequence obtained by taking the absolute values of the terms, that is mod an, also converges to 0. That is the zero test, and it's a consequence of the squeeze test. That is this. This limit is equal to 0 if and only if this limit is equal to 0. So now in place of this we have this. So that means limit of the actual sequence x to the power n will also be 0 by the zero test. Hence, by the zero test for sequence, I actually don't remember the name or number of this test. Name, of course, this is the name, but whether it's a lemma or corollary, I forgot those things, and I forgot to write it here also. But we can call it the zero test for sequences. This limit is concluded. This is also equal to 0. So that means we have taken care of this case where the absolute value is less than 1. Okay. So now next we can dispose of two particularly easy cases when x is 1 and when x is minus 1. When x is equal to 1, the sequence is the constant sequence. All of whose terms are equal to 1, and hence in this case the limit of course is 1. Okay, so this is one case, and now we look at the case where x is minus 1. When x is minus 1, the sequence is the alternating sequence which starts with minus 1 and then the terms alternate between minus 1 and 1. I don't think the name alternating sequence has been used in this text for sequences. Alternating series is there, alternating series test is there, we will see those things. But you can understand what I mean by alternating sequence. And hence, in this case, the limit does not exist. Why? We have seen already quite a few times why this sequence is not convergent, but still let us recall. You can argue like this is not convergence because this is not a Cauchy sequence. No matter how far you go down the sequence, you won't find a stage such that from that stage onwards the difference between any two terms of the sequence is, say, less than 1 over 2. That is because no matter how far you go, you will always have 1 and minus 1, and the distance between 1 and minus 1 is equal to 2. So you cannot make this distance less than epsilon if your original epsilon is less than 2. So that is why this is not a Cauchy sequence, and since we have already proved that for real sequences Cauchiness and convergence are equivalent, so that's why this is not convergent, this is divergent. In other words, the limit does not exist. Okay, now we come to the only remaining case where the absolute value is strictly greater than 1. Finally, assume that the absolute value is strictly greater than 1. Then what about this? Okay, note that because the absolute value is strictly greater than 1, x cannot be 0. Then x is not equal to 0, and what is the absolute value of 1 over x? That is equal to the reciprocal of the absolute value of x, and that is less than 1. And there is no chance for this to be equal to 0, so this is additionally greater than 0. We can in fact write that is so by what we have already proved above, this limit is equal to 0, because in the first case itself we proved that if we have a real number y whose absolute value is less than 1 and greater than 0, of course this case is being considered, so let us take greater than 0 also, then this limit is equal to 0. This case we have already proved. So using that and in place of y taking 1 over x, we get this. Okay. Now we want to prove that the limit of x to the power n does not exist. So we are going to proceed just like that previous exercise. Suppose the limit this limit exists. Just give me a moment, okay? We are having lightning here, so I want to shut down the system. Yeah, now it's okay. Then you can probably see what we are going to do now. We are going to again use theorem 6.119, the limit loss part B, by part B we have 0 equal to 0 times L. Here again we are going to get that same contradiction, that 0 equals 1. Times limit of x to the power n this is a contradiction, and prove that our supposition is wrong. Thus, in this case, the limit does not exist. So this completes the solution and the proof of this lemma 562. Next, there is one more. Not 562, 652. And this is 653. It's exercise 653 and it will ask us to also prove lemma 653. Hint, you may need to treat the cases x less than or equal to 1 and x greater than or equal to 1 and x less than 1 separately. See, you may need to treat the cases. That's what I was talking about. It's not that you have to. In general, I'm saying you write your own solution and look at the hint only if it is necessary. You might wish to first use lemma 652. That means this one that we have proved just now. 652 to prove the preliminary result that for every positive real number epsilon and every real number m greater than 0. Okay, so then what was the need to write it like this? That for we could have as well written for every epsilon and m greater than 0. Now both are positive real numbers. There exists integer n means a positive integer. Let's just mention that also. A positive integer n such that yes, this will be needed, that the nth root of m is less than or equal to 1 plus epsilon. So the hint is quite large, but we will need this hint. Okay, so let us start the solution. So we start the solution by choosing positive real number. So that means we are following the hint. Epsilon and m. So we need to show that there is a positive integer n such that this inequality is true. Okay, so let us see what we can do. For any integer, for any positive integer, m, we have this inequality 1 plus epsilon whole to the power m is greater than or equal to 1 plus m epsilon, and this is something we haven't seen yet, but it can be very easily proved. This can be proved we haven't seen, or have we seen actually? Because it is mentioned here, see the solution to exercise 561. I think it's some form in that solution. This is either available or it follows from the calculations we did in that solution. This can be, anyway, this can be proved by induction on M. And in this regard, see the solution to exercise 561. Okay, next what we do, choosing, it's quite difficult to remember these things, choosing a positive integer n greater than m minus 1 divided by epsilon. In fact, we can take greater than or equal to. It's difficult to remember these things because uh, you see, it's not like algebra where things are rigid. For example, the order of this group or the order of this element or the number of functions with this property. Such things can be remembered, but these are inequalities which have been adjusted for this particular solution. So it is slightly difficult to remember them. So if we Now choose a positive integer n greater than or equal to this. Then what happens? Let us first see that. We get so you will see that from this it follows that m is less than or equal to n epsilon plus 1, or we can also write that as 1 plus n epsilon, and by this inequality we then have that less than or equal to 1 plus epsilon whole to the power n. But there is another question: can we choose such a positive integer? If so, why? The reason is the Archimedean principle. If you go, I think we have already proved the Archimedean principle, which is this: if you have two real numbers, okay, of which x is positive, then you can always find a positive integer m such that mx is greater than y. You can use this principle to prove that the positive integers don't have any real number upper bound. In this way, if you take x equal to 1, 1 is also a positive real number, then what do you get from this inequality? That m is greater than y. We haven't said anything about y itself. Y can be any real number. So no matter how large y is, you get a still larger positive integer m. So here think of m minus 1 divided by epsilon in place of y. So you will always get a positive integer greater than or equal to this. We actually have strict inequality, but you can relax that a little and have greater than or equal to. Okay, so that means we have got this. And now what does this imply? It implies that the nth root of it implies this. Then more specifically, then by lemma 566e, we have this. At this stage, in writing this step, it may come to your mind that this type of calculations are done all the time without referring to any such results. Yes, that is true. But at least for now, since we have the results available to us, we are referring to them and seeing that actually whatever we know to be true are true, and that is coming from this type of results. In general, when you perform such calculations in mathematics, you don't need to refer to these things. Okay, they are in the background. Now we are looking at the connection for once at least. In general, we don't need to write these things. Okay. Oh, this is not actually just lemma 566e. This is something more than that. It is lemma 566d in fact. And there is another result if one really wants to refer to everything, and proposition 563. That this is less than or equal to this. Okay. So we have got the result that they have talked about in the hint. Now what about the actual proof? So let us now start. We are given what? Oh, let us recall what we are going to prove. I also forgot that. We want to prove this. It is given that x is a positive real number. Then this limit of the nth root of x as n approaches infinity is 1. That's what we want to prove. So here also, just like the previous solution, some cases will occur depending on where x is on the numbered line. So we first assume that x is greater than 1. If x is greater than 1, then the nth root of x also is greater than 1 for any positive integer n. This is a fact. And it actually comes from the solution to exercise 561. Okay, so now, but before those things, what we will now do is we will take x in place of m here. So we write for epsilon greater than 0, we have x to the power 1 over n x to the power 1 over n less than or equal to 1 plus epsilon for some integer for some positive integer capital N. Just now I was wrongly interpreting something. I thought for a moment that this n that we have here in this inequality is any n. No, that is not true. No, this n is some particular n that we have chosen like this. So that means for our x and epsilon, we will have one such n. This is not true for every positive integer n. Some capital N is there for which this is true. Okay. Then by part E of lemma 566, the nth root of x will be also less than or equal to 1 plus epsilon for all integers n greater than or equal to n. Why that is so? It is because by this part E of lemma 566, if you increase the n here, okay, then this thing decreases. The larger you have n, the smaller it becomes. Keep in mind, this is not true for all positive x. This is true for only those x that are greater than 1. If x is less than 1, then increase in n increases this power, this nth root. So because of this inequality, we are having the fact that as n becomes larger and larger, this nth roots become smaller and smaller. So this one, this nth root is already less than or equal to 1 plus epsilon. Now if you take larger values of n, then you have this inequality. Okay, so that's how we are getting these inequalities. Okay, so far this is okay. Also, from the solution to exercise 561 in the previous chapter, we have x to the power 1 over m is greater than 1 for all positive integers m. So in particular for these positive integers also this is true. Hence one minus epsilon, which is definitely less than 1 because epsilon is positive, is less than x to the power 1 over n, and that is less than or equal to 1 plus epsilon for all n greater than or equal to n. That is, if you write this inequalities means 1 minus epsilon less than or equal to the nth root of x less than or equal to 1 plus epsilon. These two, this chain of inequalities can also be written like this. The absolute value of the nth root of x minus 1 is less than or equal to epsilon for all n greater than or equal to n. So this we have come to the conditions in the definition of the limit of a convergent sequence. This implies that finally now it has started raining after so much of thunder and lightning, and now the power will go again. Okay, so this implies what? This implies that this limit is equal to 1. That means we have proved our desired limit in the case where x is greater than 1. When x is equal to 1, the sequence x to the power 1 over n is the constant sequence one. Okay, that was a big one. I was startled a little bit, and hence in this case also the limit is 1. And if in fact if you really want to continue, see, the power is gone. If you really want to continue referring to those results, you can write here C lemma five five six part E. So now the case that is left for us is this. So we are now going to assume these inequalities. Next, assume that 0 is less than x, of course, that is true always, but x now is less than 1. And in this case what we did, just like when x is greater than 1, we have these inequalities that the mth root of x is also greater than 1 for any positive integer m. Here when x is less than 1, those mth roots will themselves be less than 1. Then the mth root of x is also less than 1 for every positive integer m. Again, see the solution to exercise 561. Okay, now two cases will arise if 1 minus epsilon is less than or equal to 0. Epsilon, you see, we already chose epsilon in the beginning. So epsilon for us is any positive real number. It may be quite large also. For example, you can take epsilon equal to 2. For that epsilon also, this kind of inequalities should be true. So there is a possibility that 1 minus epsilon is less than or equal to 0. You see, ordinarily when we think of epsilon in analysis in this way, in such situations, we think of a small epsilon, but keep in mind that this part for all, no, that's not what I wanted to say. Before beginning these inequalities, we have that condition that whatever is happening here should be true for all epsilon greater than 0. That for all I am talking about. That does not distinguish between small or large epsilon, that just says that whatever we are writing here in the definition of a limit, epsilon must be any positive real number. So in fact you can take epsilon extremely large also, something like this, an unimaginably large but positive real number. For that also this thing should be true. Okay, so that's why we can have non-positive 1 minus epsilon here. So if this happens, then our job is easy. Then, because now you see 1 minus epsilon is less than or equal to 0, and the nth root of x is of course greater than 0. All nth roots are positive when we have the actual number is a positive real number, and this is less than 1 that we have mentioned here itself, and 1 itself is less than 1 plus epsilon. And unlike the inequalities here, these inequalities are true for all positive integers n. For all n greater than or equal to 1, that is for all n or so that capital N in this case can be taken as 1. If you want, you can take a higher capital N also, it does not matter. Hence, or instead of writing a conclusion here, let's now see the other case. Now assume that 1 minus epsilon is not less than or equal to 0, it's greater than 0. Since 1 minus epsilon at the same time is less than 1, this is always true because epsilon is positive. So 1 minus epsilon now is a real number lying between 0 and 1. We have by lemma 562 that this limit is equal to 0. In place of that x, we now have 1 minus epsilon because it lies between 0 and 1 strictly. And now how can one use this? Since x is greater than 0, this implies there exists a positive integer say k such that one minus epsilon to the power n is less than x. Actually we can in fact take less than or equal to x for all integers n greater than or equal to k. How do these inequalities follow from this limit? You see, in place of epsilon, now we are considering x because x is greater than 0. That's what we are saying here. And if we take this value of epsilon, then for this value also there will be a stage such that from that stage onwards this will be true. For all n greater than or equal to k, because here the limit is 0, no? And this thing is equal to this 0. Of course we understand 0 vanishes, but what about the absolute value? The absolute value also can be just removed, because 1 minus epsilon is positive, and that's why 1 minus epsilon to the power n is also positive. So that's how we get these inequalities. That is, one minus epsilon is less than or equal to the nth root of x. Again, taking nth roots on both sides, because 1 minus epsilon to the power n and x both are positive. So the nth roots also will follow such an inequality. And the nth root of this, of course, from properties of nth roots, that lemma 566 equals 1 minus epsilon itself. And keep in mind that 1 minus epsilon itself is also positive. So everything is okay, and this calculation is justified for all n greater than or equal to k. So 1 minus epsilon is less than or equal to x to the power 1 over n, which is strictly less than 1. Why? Because we are now under the assumption that x satisfies these inequalities. We have already mentioned that when this happens, any nth power of x is less than 1, and that itself is less than 1 plus epsilon for all n greater than or equal to k. That is, again, so whether 1 minus epsilon is negative or positive, I mean non-positive or positive, we have this type of inequalities here when that is non-positive, when 1 minus epsilon is less than or equal to 0. These inequalities are true for all indices n, and here they are true for all n greater than or equal to k. Thus, again, this limit is 1 when this. So all the cases have now been investigated, and in all of them this limit exists and it equals 1. So this proves lemma 563, and it ends this set of very small set of exercises. 3 of them are there only. After this there is one more section in this chapter where we will again go back to laws of exponents, and this time we are going to define this. I think, if I am remembering things correctly, we are going to define this power, where in the next section, where x is a positive real number and y is any real number. We have so far defined this power when y is a rational number. We are now going to extend that to real exponents. Okay, so that we will do, and you can guess that just like we had those rules of exponent, we will have similar things here for the most generality that is possible in real analysis for this type of powers. So that we will do in the next section, and after that in the next chapter we start studying the theory of infinite series and their convergence. So the video ends here. If you want to say something, you can of course write in the comment section below, or you can mail me at my usual address. So today is Sunday, no? That means Monday, Tuesday. On Tuesday we will have what have we seen recently? Yesterday we saw Galilean's algebra exercises. So, and I have also taken that out of the cycle. So after Galilean we have, okay, calculus. Yes. And after calculus, next Friday we will see number theory, and then graph theory, and then like that, and the cycle will continue. So that's just it for tonight. See you next Tuesday. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.